Introduction. What are you doing?
I'm studying hydrocarbons. Our teacher has asked us to read about hydrocarbons.
Oh, that's good. Do you need any help?
Yes, I'm reading but not able to understand.
We use kerosene oil for domestic use. Petrol, diesel and CNG are used in automobiles. All these fuels contain hydrocarbons. Isn't it interesting?
Very interesting. Please tell me more about hydrocarbons.
Sure. Come, let's start. Objectives. At the end of this lesson, you will be able to define hydrocarbons, understand the classification of hydrocarbons, explain alkanes, name hydrocarbons according to IUPAC system of nomenclature, recognize and write structure of isomers of alkanes, learn methods to prepare alkanes, write the physical and chemical properties of alkanes, explain the conformations of ethane. Definition. Hydrocarbons, composed entirely of carbon and hydrogen, are the most important family of organic compounds. They are the organic compounds of simplest composition and may be considered the parent substances from which all other organic compounds are derived. The hydrocarbons are conveniently classified into two major groups, open chain and cyclic. Open chain compounds containing more than one carbon atom. The carbon atoms are attached to each other to form an open chain. The chain may carry one or more side branches. In cyclic compounds, the carbon atoms form one or more closed rings. The two major groups are subdivided according to their chemical behavior into saturated and unsaturated compounds. Classification. Depending upon the types of carbon-carbon bonds present, hydrocarbons can be classified into three main categories: saturated, unsaturated, and aromatic hydrocarbons. Saturated. Saturated means that each carbon is bonded to four other atoms through single covalent bonds. Hydrogen atoms usually occupy all available bonding positions after the carbons have bonded to each other. Unsaturated. Unsaturated hydrocarbons contain either double or triple bond. Since the compound is unsaturated with respect to hydrogen atoms, the extra electrons are shared between two carbon atoms, forming double or triple bonds. Aromatic hydrocarbons. Aromatic hydrocarbons are a special type of cyclic compounds. We can construct a large number of models of such molecules of both types, open chain and closed chain, keeping in mind that carbon is tetravalent and hydrogen is monovalent. Alkanes. Hydrocarbons which contain only single bonds are called alkanes. They are called saturated hydrocarbons because there is a hydrogen in every possible location. This gives them a general formula CnH2n plus 2. The first four alkanes are methane, ethane, propane and butane. Alkyl groups. An alkyl is basically an alkane minus one of its hydrogen atom. For example, if methane removes one hydrogen, we will get methyl. Similarly, if ethane removes one hydrogen, we will get ethyl. IUPAC system of naming alkanes 1. The IUPAC, International Union of Pure and Applied Chemistry, is composed of chemists representing the national chemical societies of several countries. One committee of the IUPAC, the Commission on Nomenclature of Organic Chemistry, has set a system of naming organic compounds. The last syllable in the name of compound designates the family to which it belongs. The alkanes all end in -ane. IUPAC rules for naming the alkanes. Number 1. The name ending for all alkanes and cycloalkanes is -ane. Number 2. The parent chain is longest continuous chain of carbons in the structure. For example, the branched chain alkane is regarded as being made from the following parent: CH3, CH2, 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 CH3 by replacing an H on the third C from left with CH3. Number 3. The carbon atoms of the parent chain are numbered starting from whichever end of the chain gives the location of the first branch, the lower of two possible numbers. For the example given, the correct direction is from left to right. IUPAC system of naming alkanes 2. Number 4. Name each branch attached to the parent chain according to alkyl groups. In this case, the branch would be methyl. Number 5. Attach the name of the alkyl group to the name of the parent as a prefix. Place the location number of the alkyl group in front of the resulting name. In this case, it would be 3-methylhexane. Number 6. When 2 or more groups are attached to the parent, name each and locate each with a number. The alkyl substituent names are assembled in alphabetical order. Always use hyphens when separating numbers from words. The following is 4-ethyl 2-methylheptane. Number 7. When 2 or more substituents are identical, use prefixes such as di for 2, tri for 3, tetra for 4 and specify the location of every group. Always separate a number from another number in a name by a comma. The following is 2,4-dimethylhexane. Number 8. When identical groups are on the same carbon, repeat the number of the carbon in the name. The following is 2,2-dimethylheptane. Number 9. Sometimes you may need to go around corners and zigzag to find the longest parent chain. The following is 3,4-dimethylheptane. Preparation of alkanes 1. Decarboxylation. Decarboxylation means removal of CO2 from molecules having COOH group. Saturated monocarboxylic acid, salt of sodium potassium on dry distillation with soda lime gives alkane. Wood's reaction. A solution of alkyl halide in ether on heating with sodium gives alkane. By reduction of alkyl halides. Alkyl halides on reduction with nascent hydrogen form alkanes. Preparation of alkanes 2. By hydrogenation of alkanes. Sabatier and Sanderin's method. Alkenes and alkynes on catalytic hydrogenation gives alkanes. Kolbe's electrolysis method. Alkanes are formed on electrolysis of concentrated aqueous solution of sodium or potassium salt of saturated monocarboxylic acids. Electrolysis of an acid salt gives symmetrical alkane. However, in case of mixture of carboxylic acid salts, all probable alkanes are formed. Physical properties of alkane. State. Number 1. All are colorless and possess no characteristic odor. Number 2. Lower alkanes C1 to C4 are gases. Middle one C3 to C17 are liquids and higher are solids. Number 3. The boiling point of alkanes increases with increase in molecular weight due to increase in van der Waals forces with increase in molecular weight, that is, boiling point order. Pentane is less than hexane is less than heptanes. Number 4. Also the branching in alkanes gives a decrease in surface area as the shape approaches to spherical, which results in decrease in van der Waals forces. That is why boiling point of isomeric alkanes whose order is pentane is greater than isopentane is greater than neopentane. Number 5. The melting points of alkanes do not show a regular trend. Alkanes with even number of carbon atoms have higher melting point than their adjacent of odd number of carbon atoms. Melting point order is propane is less than ethane is less than methane. Number 6. The abnormal trend in melting point is probably due to the fact that alkanes with odd carbon atoms have their end carbon atom on the same side of the molecule and in even carbon atom alkane, the end carbon atom on opposite side. Thus, alkanes with even carbon atoms are packed closely in crystal lattice to permit greater intermolecular attractions. Density. The density of alkanes increases with increase in molecular weight and becomes constant at 0.76 gram per milliliter. Thus, all alkanes are lighter than water. Solubility. Number 1. Alkanes being non-polar and thus insoluble in water but soluble in non-polar solvents. Example, C6H6, CCl4, ether, etc. Number 2. The solubility of alkanes decreases with increase in molecular weight. Number 3. Liquids. Alkanes are themselves good, non-polar solvents. Chemical properties of alkanes. 1. Alkanes are quite inert substances with highly stable nature. Their inactiveness has been explained as: Number 1. In alkanes, all the carbon-carbon and carbon-hydrogen bonds being stronger sigma bonds and not influenced by acids, alkalis, oxidants under ordinary conditions. Number 2. The carbon-carbon completely non-polar and carbon-hydrogen weak polar bonds in alkanes are particularly non-polar because of small electronegativity difference in C 2.6 and H 2.1. Thus, polar species, that is, electrophiles or nucleophiles, are unable to attack these bonds under ordinary conditions. In spite of less reactive nature, alkanes show some characteristic reactions. Oxidation. Oxidation of alkanes gives different products under different conditions. Alkanes are heating in the presence of air or dioxygen are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. Higher alkanes on oxidation in presence of manganese acetate give fatty acids. Incomplete oxidation of alkanes in limited supply of air gives carbon black and carbon monoxide. 2CH4 plus 3O2 gives us 2CO plus 4H2O. CH4 plus O2 gives us C plus 2H2O. Chemical properties of alkanes. 2. Substitution reactions. Number 1. Substitution in alkanes shows free radical mechanism. For mechanism, see free radical substitution. Number 2. Following substitution reactions in alkanes are noticed. Halogenation. Number 1. Replacement of hydrogen atom of alkane by halogen atom is known as halogenations. Number 2. Halogenation of alkane is made on exposure to halogen plus alkane mixture to ultraviolet light or at elevated temperature. Number 3. The extent of halogenations depends upon the amount of halogen used. Isomerization. Number 1. The process of conversion of one isomer into other is known as isomerization. Number 2. Straight chain alkanes are heating with AlCl3 plus HCl at about 200 degrees centigrade and 35 atmospheric pressure are converted into branched chain alkanes. Chemical properties of alkanes. 3. Aromatization. Number 1. The process of conversion of aliphatic compound into aromatic compound is known as aromatization. Number 2. Alkanes having 6 to 10 carbon atoms are converted into benzene and its homologous at high pressure and temperature in presence of catalyst. Dehydrogenation. Alkanes are dehydrogenated on heating in presence of catalyst to produce corresponding alkenes. Pyrolysis. Number 1. The decomposition of a compound on heating in absence of air is known as pyrolysis. Number 2. The phenomenon of pyrolysis of alkane is also known as cracking. Number 3. Alkane vapors on passing through red-hot metal tube in absence of air decompose to simpler hydrocarbons. The product formed during cracking depends upon A. Nature of alkane, B. Temperature and pressure, C. Presence or absence of catalyst. Conformations. The different spatial arrangements that a molecule can adopt due to rotation about sigma bonds are called conformations and hence conformational isomers or conformers. The study of the energy changes that occur during these rotations is called conformational analysis. This is important because the structure of a molecule can have a significant influence on the molecular properties, including dictating the outcome of a reaction, although the ideas are developed for the simplest functional groups, the alkanes. The same principle can be expanded and applied to other functional groups. For alkanes, various conformations can be represented by using dash wedge notation in a structural perspective drawing. An alternate depiction is a Newman projection, which views a molecule by looking down at CC bond axis, showing the relative orientation of groups of the two carbon atoms. Conformational analysis of ethane. Conformational analysis are assisted greatly by a representation of molecules in a manner different to skeletal structure. A representation of a molecule in which the atom and bonds are viewed along the axis about which rotation occurs is called a Newman projection. In a Newman projection, the molecule is viewed along an axis containing two atoms bonded to each other and the bond between them, about which the molecule can rotate in a Newman projection. The substituents of each atom composing the bond, be they hydrogen or functional groups, can then be viewed both in front of and behind the carbon-carbon bond. Specifically, one can observe the angle between a substituent on the front atom and a substituent on the back atom in the Newman projection, which is called the dihedral angle or torsion angle. In ethane specifically, we can imagine two possible extreme conformations. In one case, the dihedral angle is 0 degree and the hydrogens on the first carbon line with or eclipse the hydrogens on the second carbon. When the dihedral angle is 0 degree and the hydrogens line up perfectly, ethane has adopted the eclipsed conformation. The other extreme occurs when the hydrogens on the first carbon are as far away as possible from those on the second carbon. This occurs at a dihedral angle of 60 degree and is called the staggered conformation. The staggered conformation of ethane is more stable than the eclipsed form by 12.1 kJ per mole, so that as one methyl group rotates 360 degree relative to the other, the compound passes through three stable staggered conformers via three unstable eclipsed forms. This barrier is small enough that at 25 degrees Celsius, the compound changes conformation about 50 million times each second. Sawhorse projection. Sawhorse projections are very similar to Newman projections, but are used more often because the carbon-carbon bond that is compressed in a Newman projection is fully drawn out in a sawhorse projection. When properly laid out, sawhorse projections are useful for determining enantiomeric and diastereomeric relationships between two molecules because the mirror image or superimposability relationships are clearer. Like with the Newman projections, a sawhorse projection is a view of a molecule down a particular carbon-carbon bond, and groups connected to both the front and back carbons are drawing using sticks at 120 degree angles. Sawhorse projection can also be drawn so that the groups on the front carbon are staggered 60 degree apart or eclipsed directly overlapping with the groups on the back carbon. Below are two sawhorse projections of ethane. The structure on the left is staggered and the structure on the right is eclipsed. These are the simplest sawhorse projections because they have only two carbons and all of the groups on the front and back carbons are identical. Assessment. Before proceeding further, let us know how much have you learned. Drag and drop the correct options. Did you know? In petroleum geology and chemistry, cracking is the process whereby complex organic molecules such as heavy hydrocarbons are broken down into simpler molecules, such as light hydrocarbons, by the breaking of carbon-carbon bonds in the precursors. The rate of cracking and the end products are strongly dependent on the temperature and presence of catalysts. Cracking is the breakdown of a large alkane into smaller, more useful alkanes and alkenes. Simply put, hydrocarbon cracking in this process of breaking long-chain hydrocarbons into short ones. Summary. Let us summarize what we have learned. Hydrocarbons are the compound of carbon and hydrogen only. Hydrocarbons are mainly obtained from coal and petroleum, which are the major source of energy. Hydrocarbons are classified as open-chain saturated and unsaturated cyclic and aromatic according to their structure. The important reactions of alkanes are free radical substitution, combustion, oxidation, and aromatization. Alkanes show conformational isomerism due to free rotation along the C-C sigma bonds. Out of staggered and eclipsed conformations of ethane, staggered conformation is more stable as hydrogen atoms are farthest apart.